Number theoretic, I guess, characterization problem, maybe you'd call it. Let's talk about what we mean by this little d function. It counts the number of divisors of any natural number. So for example, d at 6. D at 6 would equal to 4 since 1, 2, 3, and 6 are the only divisors of 4, right? So there's 1, 2, 3, 4 divisors. So that's what the d function does. Little d, I think it uses another Greek letter is more popular these days. But d at 6 is equal to 4. So it's a number theoretic function. Now we're asking which type of natural numbers, positive integers, enjoy this property, such that when you compose this d function with itself, you actually get 2. So it's a composition sort of thing. Now, this first fact here is just the definition of a prime number. Any prime number has 2 divisors, namely 1 and p itself. For example, d at 7 would be equal to 2, right? So this is almost a definition of a prime number where p represents a prime number. 1 and p are always the only divisors, positive divisors of a prime number. Now this one here turns out to be useful for this particular problem. The example I'll use will be, let's just look at 3 to the 4th. Let's say 3 is a prime number. Okay. So we have 3 to the 4th. Now the divisors, I'll just list the divisors, and these are the only ones because of the uniqueness, and 3's prime, right? So we have 1, 3 to the 1st. I like this kind of stuff because you don't really even need to know what the numbers really evaluate to necessarily. Just writing it in their prime forms is enough in many cases. But these are clearly what I'm listing right here are the only divisors. And there's 5 of them, right? And that justifies this statement right here. If this is 3 and this is 4, 4 plus 1 is 5, and that's what we have here. 1, 2, 3, 4, 5 divisors, okay? Now, the way to get started on the proof here is to realize that the very first fact, just by inspection, this definition of prime numbers implies that d of n has to equal to 2, okay? That d of n itself, that d of n has to be a prime, right? D at n has to be a prime because d at p is 2, right? So we need d at n, d evaluated in, to equal to a prime number, okay? Since d of p is 2, all right? The notation's a little slippery there. Now, notice also that if we let me just use the second fact here. Notice that if we have, let's see here, maybe I have room right here. D, let's set d at p of m. I'm going to go ahead and introduce another letter. Q is a very common letter. Q's in many number theory textbooks represents just a prime number. So let's say that in order to achieve this result right here, we go ahead and say m plus 1 is equal to a prime, y'all, and I'll use the letter Q here. And again, y'all, Q represents a prime. Okay, you see how that works very nicely right here? Because what does this imply? This implies that m is equal to q minus 1. Right? So what that further implies right here is that numbers of this form, and I'll just write it down. It's some prime, okay, raised to another prime decremented. Okay, y'all, and that's supposed to be q minus 1 right there. Okay, So these are the numbers. If you take a look and just at the properties we've developed right here, we know that this result right here that says p raised to any natural number is going to have that natural number plus 1 divisors, right? Well, q is a prime right here. So again, we're taking q to be a prime. And so this would be d evaluated at, so remember we increment this, so that'll just be d evaluated at, let me erase that. This will become d evaluated at q. Whoops, I got a smaller pen, but we'll live with it, right? But remember, q is a prime. Q is a prime, so this is equal to 2. Okay, so that the result here, the form we're looking for, the numbers, the natural numbers that have this property are exactly the natural numbers n is equal to p for p some prime, where p is a prime, and then raised to another prime number decremented. Okay, that's what we've shown down here. Okay, so this is what we're looking for. These are the only, and everything was reversible there, so it's definitely logic, if and only if, whatever you want to call it. And let's look at some concrete examples that meet this criterion. So we'll keep it in front of us here, folks. What if we had n equals to, let's say, let's do 11 to the 10th maybe, or let's see, no, let's do maybe 11. 11 is a prime. Okay, 7 is another prime, so we have 11 raised to the 7 minus 1, like that, right? Okay, and so it's very clear based on our analysis right here that d of this, let me just write it down, d of d of 11 to the 6th okay, equals to d of 7, right? Based on this property right here. But prime, 7 is a prime. 7 only has 2 divisors. So there you have it. So that's a concrete example of what we've shown. But again, this is the general form, and nothing precludes the P and Q being equal to each other. And again, if you want to check that out, folks, I'm running out of room here, but let's say, what do you want to, what prime number do you want here? Let's say your prime number was 13. Okay, let's say your prime number was 13. Then it's not hard to show it. It's the very same sort of thing. You would have D, and again, I'm picking P and Q to be the same thing, the same prime number. So this would be D at D of 13 raised to the 12th. Maybe we'll have room here. So you see, there's nothing about okay, so we would have 13 raised to the 12th power right here, where we're picking P and Q to be the very same prime. And I like this. I used to have a hard time with that, but a different looking symbol doesn't mean the symbols have different values, right? There was nothing in there where we had to assume that P and Q were distinct. Okay. Again, the same old thing, right? This would, using this result right here, you add 1 to this, and so you would get D at 13 equals to 2, right? So anyway, I thought it's kind of neat. That's it. The only numbers that have this composition function truth going on are numbers in this form of prime raised to another prime decremented. Hope you enjoyed.